Alright, so we're looking at 7.5, and this says part 1, but we're only going to worry about one part. I'll look a little bit at the second part, but it's not a big deal, and I cannot remember a time when it was actually asked about on the AP exam. Most of this first part, it's going to be few and far between if they do ask it, but I want you to have seen it in case you're going into physics or something, engineering, some area like that. I want you to have seen it before. Alright, so first things first, let's look at Hooke's law and review it. Remember, Hooke's law is F times K times X. F equals K times X, where K is a spring constant for a given spring, and X is the distance the spring is stretched past its equilibrium point, or its resting state. So this tells you how much force it takes to stretch a spring X distance past where it is at rest. So a spring has a natural length of 1 meter. A force of 24 newtons stretches the spring to 1.8 meters. So you would have to be given a piece like that, or an instance like that, for you to be able to find out what K is. And then once you find what K is, you can find the force for any other length that you need to stretch it to. The only other way would be for them to give you the spring constant. So if we find K using these pieces of information, these initial conditions, we can actually find that K is going to equal 30. So that gives us a force of 30x. So depending on how far you stretch the spring, you're going to have 30 times that distance as the force to get it there. And that means that this force is going to be variable. If this force had just been 30, then you have a constant force of 30 that's required to stretch the spring. But this tells us that the further you stretch the spring, the more force it's going to take to continue to stretch it. So how much work would be needed to stretch the spring 3 meters beyond its natural length? So we would have to integrate. Remember, work is force times distance if we have a constant force, but since we do not have a constant force, 30x here, we're going to have to integrate to add up all those little bitty pieces of work that you're doing. You're adding, for instance, you're having a little piece of work to take it to 1 inch, a little piece more of work to take it from 1 inch to 2 inch, and so on and so forth, all the way up to your 3 meters. Or centimeters. You could have gone and done that with centimeters as well to get up to 1 meter. But anyway, you get the idea. So we put everything in. We're integrating this thing. We're stretching the spring to 3 meters from 0. And our force is 30x. And dx, of course, is going to be how much we're stretching at each little individual time. Some small, small, small change in x. So when we integrate that, we're going to end up with 15x squared, evaluated from 0 to 3. And when we plug that in, we're going to end up with 135 newton meters. Now remember, a newton meter is a joule, so you can express it that way, but be careful, it has to be exactly newton meters. If it's newton centimeters, that is not a joule. Alright, so over a very short distance, even a non-constant force like we had before with the 30x doesn't change much, so work becomes just f of x times the small change in x that we're looking at over that very short distance we're talking about right here. So if we add up all these small bits of work, that's where we get the work is equal to the integral from a to b of f of x dx. Much like we've done with absolutely anything. We're thinking about the little rectangles, but the small bits of work are our rectangles, and they are over an infinitely small bit of time, or bit of distance in this case. All right, so let's look at an example, an actual applied problem that you might actually see. It says a leaky bucket that's 5 pounds is raised 20 feet. The rope weighs 0.08 pounds per foot. The bucket starts with 2 gallons of water, that's 16 pounds, and is empty when it just reaches the top. So that means we're losing a part of this water because of the leaky bucket as we go to the top, and it's empty by the time we get it to the top. So we're doing a lot of work and we're getting no water out of it. But that's just the problem. Now that has to do with the whole idea of the varying work that we're going to have to be doing. All right, so work, we're going to define the bottom is 0 where it starts, and the top is 20. And for the bucket, it's a constant force because the bucket's going to stay exactly the same. The work is just 5 pounds times 20 feet is 100 foot-pounds. That would be the amount of work done to raise just the bucket. Now the water, remember we're going to decrease this as we go up, where we're going to have 0 in the bucket, 0 weight in the bucket by the time we get to 20. So the force is proportional to the remaining rope because the bucket gets lighter as we go up. So we have 20 minus x divided by 20 times 16. Now, guys, don't get confused by that. All that is the percentage of rope that's left. Here's the total amount of rope that we start with, and 20 minus x is how much rope is left. So, for instance, when we go 5 feet up, we're going to do 20 minus x. That would mean 20 minus 5 gives us 15 over 20 gives us 3/4, and then we would have 3/4 of 16, because if the water is proportionally leaking as we go up, then at 5 feet we should have 75% of the water left, because the ratio here is 75%. But that's what we're doing, and we have to define it in terms of x. And we can simplify this thing down a little bit, look for the common factor of 4 there, and we can end up with 16 minus 4/5 x. And you can double check this by looking at it and saying, okay, well at x equals 0, the weight of the bucket would be 16 pounds. That's what we're starting off with. So at 20, we should end up with absolutely nothing for the force of the water. This is the force of the water only. Remember, we've already talked about the bucket. So when we get to the top, if we plug in 20 right here, we're going to get 16 minus 4/5 of 20. Well, 4/5 of 20 would be 16, so we get 16 minus 16, which gives us 0. And at 0, just like we found here, if we plug in 0 for x, this goes away and we just end up with 16. So it works out. All right, so the work just to raise the water now, this is nothing else. Like I said, we've already dealt with the bucket. We're dealing with the water, and we're even going to have to deal with the rope in just a second. But the work to raise the water is 0 to 20, the integral of it, 0 to 20 of 16 minus 4/5 x dx. And then, of course, we can integrate that and evaluate it from 0 to 20. and we get it's 160 foot-pounds. So it's going to take 160 foot-pounds to raise this leaky bucket of water, or actually just the water that's leaking out from here to there. It's going to take 100 foot-pounds to get the bucket up. So right now we are at the point where we know that it's going to take at least 260 foot-pounds of work, because 100 foot-pounds for the bucket, 160 foot-pounds for the leaky water, or the water that's leaking out. Technically, water can't be leaky, can it? All right, so now let's talk about the rope. Well, the rope weighs 0.08 pounds per foot, and we're going to look much like we did before, except for what's the length of the rope when we're at 0? Well, it's 20 feet. What is it when we're up here at 5 feet? Well, it's 15 feet. But it's changing as our x value is going up. So our force is the length times the length per foot, or the weight per foot. So 20 minus x, if x is 5, it's gone 5 feet up, therefore we have 15 feet of rope left. And 15 times the 0.08 will be how much weight we have to overcome to keep that bucket moving up, just on the rope. So that is going to be our varying force. And we can always check to see, at 0, 20 minus 0 would give us a length of 20 feet. Ta-da, we would have that. And when x is 20, when we've pulled up to where x is 20, then that means that 20 minus 20 would give us 0. So that means there'll be no rope to continue pulling. So it works out. And there's our actual forces, so we see that it is varying. So now we integrate to find the work. So the work equals the integral from 0 to 20 of 1.6 minus 0.08x, that's just this thing distributed through, dx. And we take the antiderivative, evaluate from 0 to 20, and we're going to get 16 foot-pounds. So in doing this and pulling this bucket of water up with a leaky bucket, we're going to do 276 foot-pounds of work. We have a part that comes from just lifting the bucket. We have a part of lifting the water weight in the bucket, leaking out as it is. And we have part of it to do the rope. Now, if this bucket was not leaking, what would change? Well, we wouldn't have to integrate to find this, because it would be a constant weight that would be moving through the whole thing. So that's why the bucket's leaking, so we have to do another integral. But if that bucket was not leaking, if it was a solid bucket that held the entire 16 pounds of water all the way up, the only thing we would have to integrate on is the rope. So if the force or the weight stays the same, there is no integral. The only thing that's going to be true is if it changes. Like with the rope, it's 0.8 pounds per foot. Well, so if there's 5 feet hanging down, the weight is different than if there's 30 feet hanging down. So that's a variable weight. When the force is variable, that's when you have to integrate to find the work. All right, so I want to pump the water out of this tank. How much work is done? Well, work, once again, is force times distance. And the force is the weight of the water. that we have to overcome to move the water. And then we have to calculate how much we have to move the water through there. Okay, the water at the bottom of the tank, and this is kind of weird to say, and this is not honestly true. The water at the bottom of the tank must be moved further than the water at the top, because as you can see, it's going down here and then up to the top. That's not technically true. The force or the work to move that it's the bottom is actually going to be more, because it's moving directly from the bottom. I'll explain that in just a second. Don't get so hung up on this. Just worry about how the actual calculation is done. All right, so consider us the work to move one slab of water. Now, the thing is, remember that water is going to sit, and I'm going back to this little part right here. Water is going to sit in equilibrium. So even without a pump, if we have a water level here, then over here in the pipe, I'm going to have a water level at that same height. So that means this slab right here is keeping water up to there. So it only has to go from here up and out. Now, eventually that is going to get all the way to the bottom, and then we're going to have to pump it the entire length plus the 4. But it offsets, and it's a lot easier to just calculate it the way I'm going to show you, as opposed to remembering that you have equilibrium for a certain part of this and all that. It's just easier to calculate using the way we're going to look at. All right, so consider the work to move one slab of water. The weight of the slab equals the density times the volume. Well, the density of water is 62.5, and then our volume is going to be pi times 5 squared, the radius of the tank, times dx, the thickness of this slab we're talking about. So that's the weight of the slab. So the weight of the slab is 1562.5 pi times dx. And the distance is going to be x plus 4. So we're literally, and this is where the whole equilibrium thing works it out. So don't think about it the way that I was talking about. Just imagine that you're just moving this thing from where it is directly up to the top of the 4 and out. So we're starting here and we're going up and pumping it out the top of the pipe. Just imagine that that's possible, because equilibrium works it out. All right, so if our weight of the slab is this, and our distance is this, remember we're starting at the top and working our way down. Our work is going to be our distance times our force. And if we want to find it over the interval, the whole distance, we're going to have to integrate, because our distance is not going to be constant. It's going to change as the water level goes down. So the the tank is full of water. So we've got water all the way up, and we're going to integrate from 0, x equals 0, to x equals 10. So we're going to pump this tank dry. So that's where the 0 to 10 comes from. And the 1562 pi is the slab of water weight, the force, and then x plus 4, like if we're talking about a slab on top of the tank here, we only have to move it 4 feet up. The equilibrium thing, don't think about it magically coming out and going up the tank. Just remember the equilibrium is going to we're going to have a force that's going to offset pumping from the bottom to get it up to the top. So automatically this part right here is up to there. And only as this water goes down is the equilibrium going to bring this side down as well. That's why we're only doing the x plus 4. I hope that makes a little bit of sense. Alright, so when we integrate, we can pull the constant out and integrate only what's left inside. So we end up with 1/2 x squared plus 4x evaluated from 0 to 10. And that's going to give us 50 plus 40, which is 90, times the 1562.5 pi. And that gives us approximately 441,786 foot-pounds of work. So the work would be 441,786 foot-pounds. That's the amount of work that it would take to pump the entire tank out. Now, if you had a pump that was a 1 horsepower pump rated at 550 foot-pounds per second, it could empty the tank in just under 14 minutes. Not something you'd ever have to remember. All right, now we have a conical tank that's filled to within 2 feet of the top of the salad with salad oil, weighing 57 pounds per cubic foot. How much work is required to pump oil to the rim and out of the tank? All right, so once again, consider one slice or slab. So the work in the y direction would be force times distance. The density times the volume of the slab times the distance would be the work involved. So we know that the density is 57 pounds per cubic foot. The volume here is going to be, since it's a very, very thin slice, we can think of it as a cylinder. We have to define and find out what our radius is. Well, we know that we have 10 feet across, which means the radius is at the top is 5, and the height here is 10. So whatever this value is, this is going to be 1/2 of it. So 1/2 the height squared times dy and we're integrating this in terms of y, so we use y for our height because that is the height of this thing. And then the distance, well, the distance, if this is 0 and that's 10, well, it's going to be 10 minus y. Now, here's the thing that would catch most of you. Most of you would think, okay, well, I've got to integrate from 0 to 10. But that's not the case. Why is that not the case? Well, the salad oil goes up to 2 feet below the top. So we're only going to integrate where we have salad oils from 0 to 8 in the y direction. So we integrate from 0 to 8 of 10 minus y times the density times the volume. And then we simplify and pull all our constants out to the front. Then we can integrate and evaluate. So the work to pump the salad oil out is roughly 30,561 foot-pounds. All right, now there is another section that I mentioned at the beginning. You can look at it. The PowerPoints are on Canvas if you want to go look at it, but it's not something that we're going to do in class. But if you're interested in it, it's just, well, I can't even remember what it's about. That's how little I've actually talked about it. But anyway, it's there if you want to look at it, but it's not something that you're going to be tested on. All right, that's all of 7.5. That's the end of Chapter 7. So let's get ready for a Chapter 7 test.